SMPS, an acronym for Switch Mode Power Supply, is a type of power supply unit that produces regulated DC output by using semiconductor switching techniques. Basically, here the regulated DC output signal is converted form of AC or DC in regulated input signal. It is sometimes also known as switched mode power supply or switching mode power supply. This power supply unit is designed to provide the energy to load from source by using switching devices. Before elaborating more on SMPS, various electrical and electronic loads are provided power using batteries. But batteries do not provide regulated power as they offer voltages of value either very high or very low. So, to obtain regulated DC output, SMPS is used. Unlike linear power supply, which uses the standard linear method of voltage regulation, a switch mode power supply is a device that performs voltage regulation of unregulated signal by using semiconductor switching methods. It is considered to be highly efficient because it lessens power consumption, thereby showing a decrease in the amount of heat dissipated. Thus, has replaced traditional linear power supply units. SMPS includes a switching transistor, power MOSFET, for the purpose of voltage regulation. During operation, the transistor switches between on state and off state in a way that when it is on, it fully conducts current with a negligible voltage drop across it, while when it is off, it tries to completely block the flow of current. Thus, switching between on state, saturated, and off state, cutoff, occurs at high frequency, and in this way, the device acts as an ideal switch. It is to be noted here that if the transformer operates at high frequency, so the device size is reduced. Hence, the overall size of the SMPS is small with less weight, which is another advantage over linear power supplies. Block diagram and working of SMPS. The major components that constitute SMPS are as follows: input rectifier and filter, diode rectifier and capacitor filter, high-frequency switch, power transistor or MOSFET, power transformer, output rectifier and filter, diode rectifier and capacitor filter, control circuit, comparator and pulse width modulator. Initially, the unregulated AC input signal from the source is provided to the input rectifier and filter circuit. Here the AC input signal is rectified to generate a DC signal and further smoothened to remove high-frequency noise component from it. The DC output, still in unregulated form, is fed to the power transistor that acts as a high-frequency switch. Here the DC signal undergoes chopping, switching. This circuit acts as an ideal switch, i.e., when the power transistor, chopper circuit, is in on state, current passes through it with negligible voltage drop, and DC signal is obtained at the output terminal of the transistor. However, under the off state of the power transistor, no current passes through it and leading to cause maximal voltage drop within it. Thus, at the output side, no voltage will be present. Hence, according to the switching action of the power transistor, DC voltage will be obtained at its output side. The chopping frequency plays a crucial role in maintaining the desired DC voltage level. The obtained DC signal at the output of the chopper circuit is then fed to the primary winding of the high-frequency power transformer. Here the step-down transformer converts the high-voltage signal into a low-voltage level, which is further provided as input to the output rectifier and filter unit. This simply filters out the unwanted residuals from the signal in order to provide a regulated DC signal as the output. The control circuitry present here acts as the feedback circuit for the complete unit. This involves a comparator along with a pulse width modulator, PWM. The DC output from the rectifier and filter is fed to the control circuit where the error amplifier, which acts as a comparator, compares the obtained DC voltage with the reference value. If the DC output is greater than the reference value, then the chopping frequency is to be decreased. The decrease in chopping frequency will reduce the output power and so the DC output voltage. However, if the DC output is less than the reference value, then the chopping frequency is increased. When chopping frequency is raised, then the DC output voltage will get increased. The pulse width modulator in the above circuit is responsible for generating a fixed frequency pulse width modulated waveform whose duty cycle controls the chopping frequency. Basically, the duty ratio is the ratio of on time to the overall cycle time, i.e., on plus off time. Hence, by making necessary adjustments in the width of the pulses, the chopping frequency gets adjusted, hence, regulated DC output can be obtained.